Hi, I'm Dr. Piyada, a lecturer in Environmental Science and Technology program, Faculty of Science and Technology, Pibun Songkram Rajkot University. In this video, you will learn that how the soil forms, what are the importance of soil component, what is the soil profile, and how to make the soil sampling and testing. Then I will tell you in deep detail about the soil physical properties such as soil color, soil texture, and soil structure. I hope you got some value in this video, and I hope it helps. First of all, I will briefly discuss how the soil evolved from the state of the source rock. This process is the same since the origins of the earth. Million years ago, the earth was made up only rock. There was no soil, no plant, and no life. Earth's rocks are broken into small pieces due to the actions of ice, rain, heat, or wind. The process of the breaking down rocks into the smaller and smaller pieces by which atmospheric and environmental agents is called weathering. Weathering breaks down rock into smaller pieces into progressively smaller particles by the effects of weather. Slowly, tiny plants and moss grows on the small pieces of the rock. When these plants die, they remain on the broken pieces of the rock. Then the soil would form. This was continual and the bigger trees start to grow up and slowly. The animal life began on the earth. Decomposing organic material from plants and animals mixed with the accumulated soil minerals. It takes more than 500 years to form an inch of topsoil. Now we can talk about soil being three phases coming together. So we have solid, liquid, and gas. If we look at the solid phase, we are going to have the mineral of the soil itself. So that was the particles that came from the parent rock. We also have the organic materials, so the living material such as roots or dead material. It also has the hydrosphere, so the water coming together. And then we are going to have the air. And this is the breakdown of how much contribute to the soil. It's going to differ on what soil we have. But if you think about it, what is soil? It is the coming together of the lithosphere or the earth on our planet. On average, soil contains 50% pore space, which contains the air or the atmosphere and water from hydrosphere. And it is also the biosphere or the living material. So that is why soil is important. It's at this interface between all these different spheres on our planet. Solid material holds or provides nutrients that can become accessible for organisms. Pore between the solid materials hold the liquids and gases that are essential for the plants and microorganism growth. The primary soil gases include nitrogen, carbon dioxide, and oxygen. The oxygen is the critical because it allows for the respiration of both plant roots and soil organisms. The formation of soil is the continuous process occurring still today from the time of the Earth's inception. If we look at how is it formed, bedrock is broken down, weathered over the time, and we eventually get what are called the horizons of the soil. You can reverse to the beginning of the video that I have described about the soil formation before. We could classify as 4 major soil horizons, including O, A, B, and Z horizons. At the top soil is called the O horizons or organic horizons. Millions of the dead plant and animal organisms are slowly decomposing, which take from 100 to 600 years to form. Below that, we are going to have the A horizons. This horizon is also called topsoil. It is a nice mix of the minerals and also all the organic matter from the horizon above, dark in color in here. As we go below that, we are going to have the B horizons, which is the subsoil. Not a lot of organic found in here. This horizon is a zone of accumulations of the fine materials and the mineral precipitate like SK, iron, carbonate, gypsum, and the nutrients that are pushed down from the soil layer above, lighter in color and more density and humidity than the topsoil. And then finally we get down to the C horizon, where we have parent rock with partly weathered rock fragments and usually yellowish color. A layer is the hard bedrock underlying the soil. The bedrock may contain cracks, but these are so few and so small that few roots can penetrate. The cracks may be coated or filled with clay or other material. Now in certain soil horizon, we will also have an E horizon. This horizon is the movement of water down. It is pulling those clay particles, minerals, and organic matter leached out of the soil and just left with the sand and silt, kind of this dry layer. The reliability of the soil test is only as good as the sample you submit. The soil sample that is being analyzed should be represent the whole field that you need to be tested in order to get a good recommendation. Inaccurate results are most commonly caused by error in sampling. If the soil samples are not taken correctly or are not representative of your field, the results and the recommendations are not going to be useful. Soil vary due to underlying geology, topography, and prior field management such as crop growth and crop rotation, fertilizer and minor application pattern, and tillage or no tillage history. So when you look at the landscape, soil are going to vary from farm to farm, field to field, and within the same field. This can all make sampling a challenge. By following basic soil sampling practices, you can minimize the effects of the soil variabilities and get the recommendations based on the average conditions in your field. The collect sample should not represent the multiple fields that have different management histories and soil types. You will not sample a field with the same management. In this example, the farm in this figure has the separate soil sample from each of the 3 separate sampling areas because of they were different soil type, crop grown, and management history. By the area A is orchard, B area is pasture, and C area is the vegetable row crop. For annual crops such as vegetable, rice, corn, the best approach is to travel across the entire area to be sampled in a zigzag pattern, randomly selecting spot to take 15 to 20 subsoil samples within the sampling area. For perennial crops such as orchard, tree plantations, etc., Take a soil sample about 8 inches or about 15 cm depth for 2 to 4 spots in the zone of maximum root activities of the select 15 to 20 trees across the entire area. To take sample, a soil probe is ideal because it takes an equal amount of the soil from all depths. So, I will show you a video how to take the soil sample by soil probe, which is described by Chris Patrick.
What I have here is a standard soil sampling auger, of which I'm going to insert into the ground up to 6 inches to gain a core or subsample. I'll then put the subsample into a clearly labelled bag ready for analysis. So now I'm going to take 25 core or subsamples across a W pattern across the soil zone in order to gain a representative sample of that soil type. So we now have finished and we have our 25 cores or subsamples into our bulk sample in a clearly labelled bag ready for sending off to the labs.
If you are using something like a trowel, weeding knife, or spade shovel, don't use all the soil collected from the shovel. Because of the shape, you are taking more soil. Instead, take a small portion or a slice of the soil from the shovel to arrive at the subsample with approximately equal amounts of the soil across the depths. Being by remove any debris on the surface, anything, any straw or pan debris. Remove that. And then you make a little face in the soil. Dig down about 6 to 8 inch or about 15 cm mark. You can take the parts of the soil sample where the plant roots will grow, and then put the sample in the bucket. This table represents the soil tests taken at the different depths vary from land use. As you can see from the shallow root crop, we'll take the soil sample at 6 inch or about 15 cm, while the perennial crop and deep root crop at the deeper depth. Results and the recommendation will differ based on the depth that you can sample to. Then, the total soil sample collected from the study field should be mixed by turn the entire sample over at least 3 times until the soil sample is thoroughly mixed. Flatten the pile to a uniform thickness and diameter. Then divide sample into 4 equal quarters, the diagonally opposites of which are rejected. Quartering is continued until the suitable sample volume is achieved. Collect the sample in a clean cloth or polyethylene bag and label with the required information. Once you have finished collecting samples in the field, soil sample preparation is needed to do before analyzed. First of all, allow soil to dry. Best practice is to lay the soil on the paper with air dry or dry soil at 105 Celsius degree for 20 hours in oven drying. Then, it needs to crush and break up any large chunk or a section of soil sample. There are many options. You can use mechanical like a rolling pin wood or plastic pipe. Then, sieving. This sieve has the bottom material to catch the sieve material, and you need to select the appropriate met site for the top. This is 2 mm met site. After the sample is broken up, Put the sample into the sieve. And give them a check. So any material that is smaller than 2 millimeters should go through the bottom of the sieve. The cloth fragments will stay on top. You will see the larger rock and root. And in the bottom of the seed is all the fine material that we will keep for the analysis. Collect and keep the sieve soil sample in the plastic container or plastic bag. Don't forget to make a clear label. Soil physical properties define movement of air and water, dissolve chemical through soil, as well as conditions affect germination, root growth, and erosion process. Soil physical properties form the foundation of several chemical and biological processes, which may be further governed by climate, landscape position, and land use. Thus, a range of soil physical properties, when altered by climate change, can trigger a chain reaction that leads to the soil environment, which may greatly influence growth and production of the crops. In this video, I will discuss about the soil color, soil texture, and soil structure. First property is the soil color. Soil color is caused by the mineral presence and by the organic matter content. Soil can exhibit a wide range of color: gray, black, white, red, brown, yellow, and under the right condition, green. Soil color is described by using the general terms such as dark brown, but can also be described more technically using Munsell soil color charts. Well, how to measure that? It's defined to 3 parts. Here is a dominant basic color, which consists of blue, green, yellow, red, and purple. And it also has a yellow-red, yellow-green, green-blue, blue-purple, and red-purple. At the top of the page, as well as the side tabs, has the hue. Number values change within the hue color chart in 2.5 increments. Within each letter range, the hue becomes more yellow and less red as the number increases. For example, 2.5 YR is redder than 5 YR. The second component is value. It indicates the degree of the lightness or darkness of the soil sample on the scale of 0 to 10. 0 equal black and 10 equal white. As you can see in the Munsell color soil chart, the lightness increased from the black at the bottom of the page to the gray to nearly white at the top of the page. Value or light or darkness reads on the left of the chart vertically. Now the chroma is represent the color intensity, saturation, and relative vibrance on a scale from 0 to 8. 0 indicates that your soil sample has almost no color, and 8 indicates your soil sample has a very intense color. On your Munsell soil color block page, chroma number read from left no color to right very vibrant color. Color notation should be noted in the following order: hue, value, chroma. As an example, the color notation 10R5/8 means hue is red 10R, 5 is the value, and 8 is the chroma. Or in another way, your soil sample color is 10R and its lightness is 5 middle of the road lightness, and in the chroma or the color vibrance is high, so it receives the highest rating of 8. A color name diagram is on the opposite page to the left, which corresponds to the Munsell chart on the right. To accurately use the month soil color chart, the user must follow proper technique when determining soil color. And now, let's see how to measure the soil color. Prepare soil sample. Soil should be moist, not wet, not dry. Normally, we should test the soil color in the field under sunlight. Use a pot to find a natural clot of soil and then break it apart and open. This is the leftover for the soil test, so that is the untouched soil and a little bit moist. If it dries, you can spray some water. For this soil sample, it's plenty wet here. Then you hold the soil behind the chart and you're trying to compare the soil by color chip the soil matches and then read the soil color. Soil texture is a summation of proportions of sand, silt, and clay content. It's an important land environmental variable because it plays a key role in soil degradation and water transport process, controlling soil qualities and its productivity. Soil texture is a very stable characteristic that influences soil biophysical properties. It is interrelated with the soil fertilities and qualities in the long term. The soil texture is associated with the soil porosity, which in turn regulates the water holding capacity, gaseous diffusion, and water movement that determines the soil health. Soil textures also determine the root system and the extent of the root litter decomposition and its rhizospheric microbial respirations. Soil texture can be determined by simple method. This video, I will describe two easy methods including field method and sediment method. To determine the soil texture by field, first step is wet and neat soil. Add 25 grams of soil to palm. Add water a little at a time. Knead soil to break down all aggregates and use spatula to help mix the soil. Knead the soil until it feels like moist putty. Second step, try to form a ball with soil. If the soil cannot form a ball, it is sand. In case it can form a ball, continue to determine. The third step, try to form a ribbon with ball. Place ball between thumb and forefinger. Squeeze upward to form a ribbon. Allow the ribbon to break under its own weight. If the soil sample is not able to form the ribbon, it is loamy sand. In case it can form a ball, continue to determine by measuring the length of ribbon. The length of ribbons is less than 2.5 cm is loam. Between 2.5 to 5 cm is clay loam, and more than 5 cm is clay. The fifth step, place some soil in palm and excessively wet. Rub with forefinger and determine if it feels smooth like flour, gritty like sugar or sand, or not too gritty nor too smooth. The loam soil type. If you feel very gritty, it is sandy loam. If you feel very smooth, it is silt loam. And feel neither gritty nor smooth, it is loam. It takes the same method in clay loam. If you feel very gritty, it is sandy clay loam. If you feel very smooth, silty clay loam. And neither gritty nor smooth, it is clay loam. And also in clay soil type, if you feel very gritty, it is sandy clay. Feel very smooth, it is silty clay. And neither gritty or not smooth, it is clay. To determine soil texture by sedimentation. Soil texture can be determined by forming a simple experiment using a graduate cylinder, plastic wrap, and a rubber band. Put a soil sample in a graduate cylinder and add water almost to the top. Cover the top of the cylinder with the plastic wrap and secure with the rubber band, and check it vigorously until the soil and water thoroughly mix. Then let the cylinder sit overnight. The soil grains settle based on their size. The larger sand grains settle out first and form a layer on the bottom of the cylinder. The fine grain still form the next layer, followed by the very fine grain clay. The volume proportions of sand, silt, clay can be determined using the marks on the graduate cylinder. This particular sample is 25% clay, 35% silt, and 40% sand. The data for our soil sample indicate that it is loam. Soil structure refers to the grouping and arrangement of soil particles of sand, silt, clay, organic matter, and fertilizers aggregate into bed. The arrangement of these aggregates separated by pores and cracks. There are actually 6 types of soil structure that you can have. The first structure is granular structure. These fine particles with the size of 1 to 10 millimeters, which are actually stuck together by organic matter and fungal hyphae and things like that, give you a good granular structure. So, the more organic matter that you have, the better granular structure is going to be. This is the most desirable soils to have on the soil surface. The next structure is platy. Looks just like a series of the thin plates or sheets fly horizontally on the one another. It is commonly found in the parts of the A horizons and in the clay pen soils due to the tilling of soil below normal pore depth. These soils have lots of plate structure, which are going to have poorly drained soil situation. The next type of structure is called blocky structure. These shapes are cubes-like. The size of blocky soil structure is around 5 to 50 centimeters. Soil structure can be separated into 2 types, angular blocky and subangular blocky structures. Subangular blocky structure. The edges of block are actually rounded off, versus angular blocky structure have sharp angles. They are commonly found in the bay horizon where clay has accumulated. There is a moderate water and air permeability and distribution of the root crop. The prismatic structure. Soil particles have formed into the columns in vertical direction in the sharp edges. They are commonly found in the bay horizon where clay has accumulated. The size of the structure unit is around 10 to 100 millimeters. There is moderate water and air permeability. Similar to prismatic structure, but prismatic tops are rounded. Found in bay horizon, especially in arid climate with high amount of exchangeable sodium. The last soil structure is single grain, where the individual soil particles, soil that not stick together, away accompanies a loose consistence, commonly found in sandy soil, which move freely in water and air.